Hello, everyone, and welcome to video A for related rates. There's going to be 3 videos on this particular topic. So today we'll just be doing questions 1 through 5. The first one says, a snowball is melting at a rate of 2 cubic feet per hour. Some days I get lucky and I teach this when there's actually snow on the ground. But of course, I have no idea what day you're watching this. So I've got myself a nice snowman here. And eventually, as you can imagine, it starts to, fall apart until you have just that one big one left in the yard. Can you picture it? So you leave for school and you've got this giant snowball in the yard that's just the bottom remains of your snowman. And then you come back, and even though the sun's come out and maybe all the area around it has actually turned into nice green grass, the snowball looks pretty big. And eventually, the snowball looks smaller and then smaller. And then one day, it literally seems like it goes from a pretty decent snowball to nothing. Why does that happen? Because the volume is changing at the same rate. So if every single time it's melting at a rate of 2 cubic feet per hour, when you have a good size radius, that 2 cubic feet is not going to hardly show up. Let's say it takes, I know it won't take it off the bottom, but let's just say it takes a little bit off the whole area. When you have a smaller radius, then that same volume cuts much deeper into it. And when your radius is really small, the whole thing can just go away. This is what we call related rates. The volume rate, that which is decreasing, is definitely related to its radius rate. And that's what we're going to be studying in this problem today. So I know with modeling and optimization, kids really like those because there's, 7 very distinct steps. And if you just follow those steps, you'll get it every time. These aren't quite as clear, but I will tell you that my first step is to figure out what you've been given. So when you see cubic feet per hour or per any time, that cubic is going to represent volume. But since it's per hour, now it's a derivative. It's the change, the derivative in volume. And what's it with respect to? Time, dt. You need to be able to find this little piece of the equation and give it a label. If it remains spherical, at what rate is the radius changing? So we're talking about the radius, but we're talking about its rate of change. So we're going to call that dr dt. So your first step is to go through and identify the variables that you're looking at. Actually, we're going to take care of one little thing here first, and that is we can't have feet and inches in the same problem. We do need to convert that. So I have my 20 inches here before I go any further. 20 inches, my conversion factor, I want to get rid of the inches, so I put them on the bottom. I want to change them into feet. So there are 12 inches and 1 foot, so that's my conversion factor. So now I have 20 over 12, which reduces to 5/3 feet. We'll be using that number instead of the 20 inches. Okay, so my step 1 would kind of be identify your variables. My step 2 would be to write a formula for the main thing you're talking about. So we're mostly talking about volume here. There is a part 2 question. We'll do that second. So volume of a sphere is something you need to memorize if you're in AP and something that you need to put on your appendix if you're in honors. It is 4/3 pi r cubed. If you take the derivative, you would write v prime is equal to, don't write this, 4/3 pi, I was so intent on telling you not to write it, 4/3 times 3 pi r squared. But we're so used to this notation, and I love it. I agree with you. V prime is a great way to write it. But if you were to write it as dv, what would be the bottom? What letter are you taking the derivative with respect to? You're taking it with respect to dr. The problem is we are talking about dv dt and dr dt. We don't need dv dr. So this is where you're actually going to learn the chain rule. I know we briefly talked about the chain rule earlier, but this is usually the unit where kids really grasp why we need it. Because we have a dv-dr, but we need a dv-dt and a dr-dt. So your step 3 is going to make a chain rule using all the pieces that you have. So I have a dv-dr, a dr-dt, a dv-dt. Let's make a chain rule. So let's see, I can do dv, let's see, if I put the t on the bottom, that should work. Because then I can do dv dr times dr dt. And look, if I did do that and I crossed off the drs, I'd have dv dt is equal to dv dt. Did I explain to you exactly how I did it? No, because it's a little bit of a puzzle. It's never going to be exactly the same. Your goal is just to make the two sides be equal. Once you have the chain rule, this problem is going to be a piece of cake. Step 4, you can fill it in. So dv dt I know is 2. I guess I went a little too high there. dv dt is 2. dv dr is, these cancel, 4 pi r squared. And dr dt is actually what I'm looking for. What is the rate with respect to time that the radius is changing? So in other words, when you have this giant snowball and it's losing 2 cubic feet per hour, it doesn't lose it in a chunk. It loses it over the radius. So if the radius is 20 inches, how fast is that radius changing? That's what this is going to tell us. Oops. All right, so let's solve that. We'll move it up here. So 2 divided by 4 pi r squared is equal to dr dt. That's my formula. That means you tell me the radius, I'll tell you how fast it's changing. And now let's go back to my opening picture. When the snowball is huge, let's say the snowball is, I don't know, let's be really drastic. Let's say it's 3 feet in a radius and it's losing 2 cubic feet per hour. The change in that radius in an hour is going to be 2 over 4 pi times 9, 2 over 36 pi. It's tiny. You're not even going to notice it. But when it's what we have, which is 5/3 of a foot, think about how much different that's going to affect it now. Now it's going to be 2 over 4 pi times 5/3 squared. So this actually reduces to 1 over 2 pi times 25 over 9, which is, if you flip it, 9 over 50 pi. That's the rate at which the radius is changing. If you were to actually make that into a number, it would be negative 0.057 feet per hour. Notice that the volume is in cubic feet, but the radius is just in feet. So those are the steps for a related rate problem. We actually have 2 problems in one here, because now they ask for at what rate is the surface area changing. So they want the derivative of the area as time goes by. So step 1 is to identify your variables. Step 2 is to get an equation of some kind that you can use. Well, I know that surface area, I'm just going to write A for area, is equal to, of a sphere, 4 pi r squared. All right, I have to take a little side note here. On the outside chance that you noticed, hey, we already had 4 pi r squared. So I'm going to tell you something that hopefully will sound really cool. So the formula for volume, little break here, is 4/3 pi r cubed. The derivative of volume with respect to r is 4 pi r squared, which is the surface area. That's because if you want to change the volume, the change in volume is going to be like adding a layer of surface area. Does that make sense? It works for other things too. Let's say you have the area of a circle. Area of a circle is pi r squared. What's the derivative of the area of a circle? It's 2 pi r. Does that formula look familiar? That's because if you have the area of a circle and you want to change it with respect to its radius, how would you do that? You'd add a layer of circumference, and that would change its area. So yes, if you recognize that formula, good job for you. You were spot on. That's exactly what we want to be doing. So back to our problem, dA dr is 8 pi r, but we don't want dA dr, we want dA dt. So what did we do last time? We thought of a chain rule that connected the things that we knew and dr dt with the things that we want to know. So my chain rule is going to be dA, and you have to figure it out, like, do I want the dr here or do I want the dt here? Because I have two choices, right? But I need the dr to end up on the bottom. And if I look at the three that I'm working with, the dr is going to be on top. So I have a dr dt, which is never going to happen. So I'm actually going to make this the dA dt, because that way the dt is on the bottom. And if I can just get dr to cancel, I'll be good. And can I do that? Yes, with dA dr. So dA dr times dr dt would reduce to dA dt. So this is my chain rule. Although I don't actually want those crossed off. I was just trying to show you that it works. So dA, I'll just rewrite it. dA dr times dr dt. Okay, step 4, let's fill those in. dA dt is what I'm trying to figure out, the rate of change of the surface area. dA dr is right there, 8 pi r. And dr dt we've already discovered. dr dt, right there, although I'm going to use, the reason I left it in this format in the first place was because I knew I was going to use it, and I didn't want to have it already converted to a decimal. You never want to round off a decimal when you're still in the middle of a problem. You need the original number. So 9 over 50 pi. So the derivative of the area, the change in the area as time goes by, the pi's cancel, and it's going to be, let's see, we can reduce that even a little bit more. So divide by 2 is 4 over 25. So 36 pi. No, there's no pi. 36 r over 25. 36 r over 25. This is a general formula. We want to know how fast the surface area is changing at a very specific moment. We want to know how fast it's changing at the 5/3. And actually, I've already used that number here. This answer was only good at 5/3 feet. So the correct way to do that is dA dt. You draw a line. You've probably seen your calculator do it this way. And then put the 5/3. That lets somebody know that you're plugging in 5/3 for r. So 36 over 25 times 5 over 3. These cancel, and you get 12 over 5. What's the unit on that? If it's area, hopefully you thought in your head square feet. And because it's dA dt, the area is square feet, but the time is in hours. So believe it or not, neither of these answers are completely correct. We are missing something. You either have to add a negative to show that the radius is decreasing when the snow is melting, or you have to say the radius is decreasing at a rate of 9 over 50 pi. You don't have to do both. That would be a double negative. You wouldn't want to say the radius is decreasing at a rate of negative 9 over 50 pi. But either say that the radius is changing at a rate of negative 9 over 50 pi. That implies that it's decreasing, or just use the word decreasing. It's really up to you. But you do have to do the same thing here. The area is decreasing at a rate of 12 over 5 square feet per hour. So up to you, but make sure you have that sign in there. If you're thinking, what if I didn't think of that? How should I have known that? Well, some people put it in the original equation. So at this point, when it said the snow was melting, you could have made this negative, and then the answer just automatically would have come out negative. Other people don't like the negative in the problem because negatives are sometimes a cause for mistake. And so they'd rather just know if something is increasing or decreasing and add it at the end. But some people forget at the end. So you have to decide which way works best for you. All right, I will warn you that on question 1, you can see you're now able to do 1, 2, and 3 on the worksheet. Question 1 is trickier only because they skip this middle step. They go straight to, here's the volume at which it was melting, tell me about the surface area. I'm just going to tell you right now, you can't get from volume to surface area. There's nothing in the volume equation about surface area. You need to use the radius as a middleman. Radius is in both the volume equation and in the area equation. So number 1 is almost the same, but they don't write this middle sentence, and you really need to know to do that on your own, which is why it's not there, because you need to be thinking, how can I connect these? So a little warning there on number 1. All right, let's do number 2. A small funnel in the shape of a cone is being emptied. So this time I'm going to do it the opposite way. I am going to put the negative in, just trying to give you guys choices. So it's being emptied at a rate of 12 cubic feet per second. 12, I said cubic feet, cubic centimeters, cc's, per second. It is negative because it's being emptied. The volume is decreasing if it's being emptied. And the way you know what this unit is because cubic centimeters is a volume and the rate is in seconds, which is a time. So it's going to be your dV dt. The height of the funnel is 20 centimeters. And the radius of the top is 4 centimeters. How fast is the fluid level dropping? So that as soon as they say how fast, you know you're looking for a derivative over time. How fast is something happening? Your goal is to identify what it is they want you to measure. We already know the volume. Do they want you to measure the area? Do they want you to measure the height? When somebody says, how fast is the fluid level dropping, they're talking about the height inside the funnel. So dH, it changed, dH dt. And then it says when. Okay, this is really important to me. The when you're going to save for the end. You can't put a 5 in the middle of the problem. At the very end, when you have your formula, dH dt, then we'll evaluate it at 5 centimeters, but not before then. So this problem is going to kind of harken back to the one that we did in modeling and optimization. You might remember where we cut this off, and I explained how this was a similar triangle to the overall cone. We're going to do the exact same thing, but it's going to be easier because we actually want to deal with the piece that's left. If you recall, before we were dealing with a cylinder inside of cone, so we were trying to work with this similar triangle, even though we really wanted to talk about the cylinder. So it was a little bit harder. Here, we're going to be talking about a cone and then another cone. So we're going to be talking about them as similar things. So how fast is the fluid level dropping? We're going to measure H, and it has its own R. So they are similar. So 4 is to 20 on the original funnel. But if the water is only this high, then it has a radius and a height that will be similar to the overall funnel. So we have now a constraint added into the mix. Now let's see, what do we have? We have dH dt, so we've identified that variable. We have dV dt, but normally, remember step 2 is to write your main equation. The volume of a cone is 1/3 pi r squared h. This is where the constraint comes in. We need it to have just one variable. But this is important. Which one do we need to leave in there? We need the problem to be discussing h. So the h has to stay. The r has to go. So I'm going to, even though the r is being squared, which we wouldn't normally do. So I'm going to multiply both sides by h to work with my constraint. And I get 4h over 20 is equal to r. I'm just going to reduce that to h over 5 is equal to r. So this becomes 1/3 pi h over 5 squared times h. So the h squared can be put with the other h to make h cubed. And the 25 can be put with the 1 over 3 to make 1 over 75. If I took the derivative right now, I would be doing so with respect to h, which would give me 1 over 25 pi h squared. Now that you have found your main equation dealing with h, now is when you look for that chain rule. I know dV dH, I want dH dt, and I know dV dt. Can you form a chain rule that involves all three of these? Go ahead and try. Don't just wait for me. I think to myself, I need the dV dt on bottom, and this one's on bottom. So I'm going to do that. And then I'm going to write this one, which means I need the dH to cancel, which I can do if I put it on bottom. And I have one where it's on bottom, a little puzzle piece going together there. So are the two sides the same? Yes, because the dH cancels, the two sides would be the same. So I've made my little chain rule. And the next step is to fill it in. dV dt is -12. dH dt is what I'm trying to find. And by the way, since dH dt is what you're trying to find, that unfortunately is how people try to start their chain rule. They're like, okay, so I'm trying to find dH dt. And then they try to form their chain rule with this, and then they get stuck. You can do it. It would be dH dt, or sorry, dV dt divided by, I mean, you can make a different puzzle, but it's definitely a little tricky that way. So I don't recommend it. Times, and then dV dH, which is right there. 1 over 25 pi h squared. -12 is equal to dH dt times, let's see what's the best way to do this. I think I'm just going to multiply both sides by 25 over pi h squared times 25 over pi h squared. So my dH dt is equal to, what was that, -300 over pi h squared. So does it make sense that it's negative? Absolutely. If the volume's going down, then the height is also going down. So what have I found? I have found a formula for the height of this at any time. You tell me, or the rate at which the height is changing at any time. If you tell me the height, I'll tell you how fast it's going down. Now, what makes more sense? When the volume is near the top, it's almost filled, is the height changing very rapidly? Not at all, because it takes so much for it to lower when it's only losing 12 cc's per second. But when it's really close to the end, when it's only this full, it's going to really start to go fast at the end, which makes sense. If h is a bigger number, because it's being divided, this overall thing is going to be a bigger number. All right, let's go ahead and plug in the one that we want. dH dt, do you remember the correct notation? At, and was the units all the same? Centimeters, how fast is it standing when it is 5? So at 5 is negative 300 over pi times 25 is equal to negative 12 over pi. What units do we have? This is the height, so it should be measured in centimeters, and it's the derivative of time. So per, in this case, second. And that's my answer. That's how fast the fluid level is dropping. So you're identifying all your variables. You're using a constraint on some problems. We didn't need one on the last one, but you have a main equation that you're dealing with. Once you get your main equation, you can form your chain rule and fill in all the pieces, and you should be done. Okay. Let's do number 3. Sand is poured onto a conical pile. So you can probably picture this, right? You're at the beach. You're pouring sand onto your pile. Keeps getting a little bit higher. The rate is 20 cubic meters per minute. As soon as you see meters cubed, you should be thinking volume because it's cubic. And per minute should make you think that it is going to be your dV dt. Identify your variables. The height of the pile is always equal to the radius of the base. So the height is always equal to the radius. So as you try and keep making your sand pile taller, can you picture it? You're making it a little bit taller, but it's also going to keep spreading out. As much as you would love to maybe have a certain radius and build a tower, it's really hard, right? Because as you pour the sand onto there, it's going to keep getting wider and wider as well. So the height is always equal to the radius of the base. When, all right, as soon as I see the when, remember you're going to save that for the end. When the pile is 3 meters high. So I'm going to be doing something at 3 meters. How fast is the height of the pile increasing? You need to be able to change that to a variable. How fast means it's a derivative. Is the height means it's dH over time. dH dt. So I'm going to find dH dt, but then I'm specifically going to find it at 3. But the when part you're saving for the end. You want to work with a general formula. So I have 2 pieces of my chain rule. What am I missing? I'm missing my main equation. So my main equation is volume of a cone, 1/3 pi r squared h. I can't have 2 variables. I do need to keep the h, but fortunately, much easier than the last one, h and r are always the same. So I actually can change this, h is equal to r, to just volume is equal to 1/3 pi h cubed. Wasn't that handy? If I take the derivative of this, what variable is going to change? Not t. I don't know dV dt. I can only do dV dH, which if I bring down the 3, that makes the 1/3 go away. So it's pi h squared. And now do you see it? I have my 3 parts to my chain rule. Go ahead, see if you can put it together without me. Did you get it right? I hope so. There's my chain rule, and now I'm going to fill it in. Hopefully at least one of you just went, I get this. I like this. I hope so. So this is changing at a rate of 20 cubic meters per minute. So 20 cubic meters per minute is dV dH, which is pi h squared, times dH dt, which is what we're trying to find. So it looks like there's 2 variables. There are. We're trying to solve for dH dt, but it's going to have an h in it. Why? Because it's going to keep changing based on what h is. So when your h is really small, right, really, really tiny, the height is going to grow fast. Because think about it, if it's like a fraction down there, so if it's 1/100th, if it's really tiny, it's not going to flip and multiply it, so it's actually going to be really big. So when the height is small, really small, you're going to be able to grow it really fast. In the beginning, you're making your pile at this beach, you think you're doing a great job. But then when the H gets to be too big, then this rate at which the height is increasing, you literally have this huge pile. You come and you pour some more sand on it, and it feels like it didn't grow at all. So the rate at which the height changes is completely dependent on how tall it is already. What do we want to know it at? 3 meters. So dH dt at, here's the correct notation, at 3 is 20 over pi times 3 squared, which is 20 over 9 pi. What are the units for that? Well, we're looking at the height. So the height would be measured in meters. And the minutes, not hours, not seconds. You always just have to check meters per minute. And there's your answer. The next one is a little bit different. It's going to have like a little bit of a shortcut to it. So number 4, the top of a ladder, of a 25-foot ladder, leaning against a vertical wall, is slipping down that wall at a rate of 1 foot per second. So this y, how high the ladder is changing at a rate of 1 foot per second. And it's going down, it's slipping down, so -1. How fast is the bottom of the ladder slipping away along the ground? So does it make sense that if the ladder is slipping down in this direction, it's also got to be slipping out in this direction? So x is changing. How do we represent change? By dx dt. That's how we represent change. How fast is it changing? This is our variable. This is what we want to know. We have a 25-foot ladder. So the question is, what equation connects these different pieces? And on this one, it's a little bit different than what we've been doing. It's just the Pythagorean theorem. X squared plus y squared is equal to h squared, the hypotenuse squared. So I do x squared plus y squared is equal to 25 squared, which is 625. Now this is where where we can take a little bit of a shortcut. So if I did this right now, the traditional way to do it, do not write this down. I'm just going to show it to you really fast. Y squared is equal to 625 minus x squared square root, and then you would find dy dx, which is equal to 1/2 625 minus x squared to the -1/2 times -2x. And now you could use your chain rule. You've got your dy dx, your dx dt, and your dy dt. This would work. There's nothing wrong with this. However, there is a little bit of a shortcut that you can take. It actually works on all problems, but that is just too annoying to work with as square roots to negative, fractional exponents and things. Watch what you can do instead. You can kind of do implicit differentiation. I can do 2x and take the derivative with respect to t. But since I'm doing it with respect to t, the derivative of the inside, so I bring down the 2, now it's x to the first, the derivative of the inside is dx dt. This is like implicit differentiation. And on this one, I bring down the 2, I have y to the first, and the derivative of the inside is with respect to t. And the last side is just 0. How neat is that? Much tidier. So now I just fill everything in. 2 times x times dx dt, this is what I'm going to be trying to solve for, plus 2 times y times dy dt, which I know. Okay, so the question is, what is x and y? So this is the answer, but I'm going to fill in at a certain point. So at when the ladder is 7 feet away. So at x is equal to 7, This is 7. So how do I get that y? Well, unless you happen to recognize a perfect Pythagorean triple, 7, anybody? 7, 24, 25, then you'll know that this is 24. But most of you aren't going to remember your Pythagorean triples. So you're going to do x squared plus y squared is equal to h squared. So 7 squared plus y squared is equal to 625. And when you solve that, you will get y is equal to 24. So y is 24. That gives me 14 dx dt is equal to, that's negative 48. When I bring it to the other side, it's positive 48. So dx dt specifically at 7 is equal to 48 over 14, which if you divide by 2 would be 24/7. And what is its rate? It's a rate, so its unit would be feet per second. That's how fast, if it's falling at a rate of 1 foot per second, it's actually sliding away at a rate of 24/7 feet per second. So you can do it the traditional way, but this little implicit guy is a nice little workaround. All right, we're going to do one more on this video, and then that'll be it for today. It's just another ladder one. A ladder, you can try it on your own. 10 feet is the answer if you would like to try it on your own. A ladder leans against a vertical wall with the bottom of the ladder 8 feet from the horizontal wall. At that time, so they tricked you. They want you to fill it in. I don't want you to fill it in. It's when the ladder is 8 feet, even though it didn't use those words when. I want you to recognize that it's always changing. They're specifically asking you about 8. At that time, the bottom end of the ladder is being pulled away at a rate of 3 feet per second. So dx dt, I don't know who's pulling this ladder. It's very unkind. 3 feet per second. And the top of the ladder is slipping down the wall. So how is y changing? It's getting smaller, so it's negative 4 feet per second. And all of this is happening at x is equal to 8. At x is equal to 8. How long is the ladder? H for hypotenuse. L is a little tricky. So I'm going to set up my Pythagorean theorem again. X squared plus y squared is equal to h squared. I'm going to use implicit again. 2x dx dt plus 2y dy dt is equal to 2h. I can keep doing this. 2h dt. Now you might be thinking, hold on. Isn't the ladder a fixed amount? Isn't that going to come out to be 0? Yes, it is. So even though we don't know h, we do know that the rate of change of h, how is h changing as the ladder slips down the wall, is definitely 0. So last time we said 0 because we saw it was a number, and of course the derivative of a number is 0. This time, even though we don't have that, we still can, sorry, let me try to move this. We still can write that as 0. Now, hopefully at least one person's going, but I'm trying to find h and this just canceled it out. Don't worry, we got it. So at this point, x is 8, dx dt is 3, and that's positive because it's slipping away. And y is leans against the bottom of the 8 feet from horizontal wall. Time ladder is being pulled away. I don't know why. That's what we're going to solve for. And it's slipping down at a rate of negative 4. So 16 times 3 is 48. So I'm going to subtract 48 from both sides. So I get negative 8y is equal to negative 48. So I wasn't actually able to solve for h, which is what I wanted, but I was able to get y. And at that moment, now you can figure out the length of the ladder. If this is 6 and this is 8, anybody recognize this Pythagorean triple? It is another famous one. 6, 8, 10. The one you probably remember from geometry is 3, 4, 5. But then any multiples of those to scale, so 6, 8, 10, or 9, 12, 15, all also fall in that same category. So 10 feet is the length of the ladder. So we've done 5 problems. There's a whole bunch of problems that you can do now on the worksheets. If you're in AP, just start going for it. If you're in honors, I'll assign you specific ones. Obviously, you don't have to do all of those. Have a great day.